All right, guys, so as you've noticed, what we're kind of doing now is we're talking about how to take derivatives of different functions that are not polynomials. And what we're going to be talking about today are exponential functions and how to find the derivatives of those types of functions. This is one of the easier ideas we talk about, and we'll discuss why in just a second. But before we do that, what we need to do is we need to talk about what an exponential function is. Now, an exponential function, and you've seen them before, exponential functions are simply functions that you have a number raised to a variable power. And the key is that there is a variable up in the exponent. It might not just be x. It might be like 3 to the x squared plus 2x. But notice that there is a variable that is in the exponent, okay? And so that is honestly what an exponential function is. Now, the other thing that we need to understand in order to move forward is there is a specific number that we use quite often as what is called the base number. 5 in this case is the base number. It's the number that's being raised to an exponent power. 3 is the base number here. So when I look at the base number that we're going to be seeing an awful lot in this class, e is that number. Now, what confuses most people about e is it is a letter. And so most people, when they see a letter, think, okay, that is some sort of variable, because a letter always represents an unknown. This is the one case, well, there are a few others, but this is the one case that you'll see regularly where e, this letter, is actually a number. And where it comes from is if we took this formula, and you learned about this when you were talking about things that compound, interest that compounds when you invest it, that kind of thing. When we have this formula right here and we make the number n really, really, really large, like I'm talking like massively huge, millions, trillions, it wouldn't matter what the other letters are when we plug those things in. We would get the same number every single time if we were to make n sufficiently large, and we would get 2.71828. And mathematicians notice that that happens an awful lot. This isn't the only place that that number pops up. It actually pops up in a lot of other places as well. But since that number shows up so often, we call that the natural number, and they just use the letter e for that. This number shows up a ton on the non-calculator portion of the AP test. So I thought it was important to talk briefly about what e is. Now, another thing that's true about all exponential functions that you need to know for the AP test is anything, we've talked about this before, but anything raised to the 0 power is always 1. No matter what, if you take something and you raise it to the 0 power, it doesn't matter what the base is, it becomes 1. Okay? That's very important on the AP test because they do expect you to know that. The other thing is we are going to be looking at exponential functions a lot, specifically e to the x. E to the x, if I had to evaluate that and plug a number in, like e to the third, there's no way to do that without a calculator. So you are expected on the AP exam to actually leave your answer like that instead of trying to figure out what e to the third power is. There are a few other rules, and you can see them here. We'll talk about them more as we get closer to the AP test. But when you see e with e to the third or e to the fifth, you just leave your answer like that. You don't need to know what number that represents. Now, for the derivative part. You're going to like this a lot because it's really easy. But the derivative, if we look at the graph of e to the x, if I were to graph the derivative of e to the x, you'd be like, okay, it's always increasing. It increases slowly, then it goes up and up and up. And you would notice right away that the graph looks virtually identical. And so when we look at something like this, you're like, okay, I know it looks very similar to e to the x. In fact, and it's one of the nicest derivatives that exist out there pretty much, the derivative of e to the x is actually, and it's the only function that this is true for, the derivative of e to the x is e to the x. And that might seem like the easiest thing in the entire world, and it is, but it has huge implications for a lot of things in more advanced calculus. You can make a lot of, not assumptions necessarily, but you can do very advanced calculations with derivatives knowing that that is the case. It's not something that we have to worry about here, but know that the derivative of e to the x is e to the x. Now, if we have a number in front of e to the x, like here we have 5e to the x, what we do is you just leave that number out in front if you're trying to find the derivative, and then you write the derivative of e to the x, which would be e to the x. So the derivative of 5e to the x is 5e to the x. And then if I'm taking the derivative of the sine of x, I would just do that separately because that is a different term. So my derivative here would be 5e to the x plus 2 cosine of x. Again, the derivative of an exponential function is really easy to find. Of all of them, it is probably the easiest to find out there. If I wanted the 224th derivative of e to the x plus 4, you'd be like, well, the first derivative, the 4 goes away, and then the derivative of e to the x is e to the x every single time, so my derivative would be e to the x. Now, you're probably asking, okay, that's really easy, and it is really easy. So there are mistakes that get made often with e to the x, okay? The biggest mistake comes from seeing something that's e raised to something that's not just plain old x, like x squared or x to the third. We can still take the derivative of those things. We just have to understand that the chain rule is being applied. So the way that the chain rule works with exponential functions, specifically e raised to something, and that's all this is saying, this is e raised to whatever, okay? That's what this formula is saying. What we do to take the derivative of that is we raise the e to the whatever power, keep it the same, and then we multiply by the derivative of what is up in the exponent. So really, it's still e to the x. Some people get a little bit confused by that because some things they look up there and like, how am I supposed to deal with that? We always leave it by itself to start with, and then we multiply by the derivative of what is up in the exponent. So if I had something like e to the 3x and I wanted to find the derivative, I would say that it's e to the 3x. Again, I copy it down exactly how I see it because the derivative of e to the x is e to the x. But because this is a chain rule problem, I multiply by the derivative of what is up in the exponent, and then I have found my derivative. So if I had e to the sine of x, my derivative of that would be e to the sine of x, because I'm applying the chain rule and taking the derivative of the first part. Then I multiply that by the derivative of the sine of x, which is cosine of x, and I'm all done. The derivatives of exponential functions, again, still follow the same rules that we had before in that I have two different functions multiplying here together, so I can use the product rule. So I would write down my first function, then I would multiply that by the derivative of the second function. Now, where people get a little confused here is because the derivative of e to the x is e to the x, it's sometimes kind of hard to keep track of what you have and have not taken the derivative of. That's why it's so important that we follow the steps of the chain of the product rule. And that's what I'm doing here. I've still got e to the x, that's my second function, multiplied by the derivative of my first function, which would be that. Okay? So again, that would be my derivative. I apply the chain rule while I'm using the product rule, and it still finds us the derivative the same way that we normally would have. Now again, I think exponential derivatives, especially e to whatever it is, having e be the base number, is probably the easiest type of derivative that we have. So hopefully that made sense. If you have any other questions, please come on in and I can try and answer those.